thank you very much, Martin, for that great introduction. And yeah, there are a lot of winding routes into geology. I'm just glad I found one of them, and it's taken me a long way. And so, like Martin said, I'm currently in my role here in the state. I'm at DOGAMI, and I'm leading the mapping program, and we have a great mapping team. And one of our projects that I'm the lead on is out in southeastern Oregon at McDermitt caldera, right on the Nevada border. So we're going to talk about that today. Lots of other interesting work in the state. I'd love to come back and talk more about those projects maybe next year, but we're gonna focus here in on southeastern Oregon and Nevada. And so before I jump in, I just want to highlight sort of our agency and our different roles. And I know we've had Vanessa Swenton and Rich Walker from our survey come and do a couple of seminars earlier in the term. And this is kind of just like a overview of the agency and how we're divided up. But really, the point of this is that we do a lot of geologic mapping for a lot of different reasons. And so I'm here today to talk about sort of mineral resources, but really mapping is how we do a lot of what we do in the agency, which is with the goal of providing earth science information to keep Oregonians safe and prosperous. And that means mapping for hazards, water resources, energy and mineral resources. And we have this new focus area on decarbonization geoscience. So, what we're talking about today is going to be a lot of what the mapping team does, but with a mineral resource angle on it. And most of our mapping in Eastern Oregon is either geared at water resources or mineral resources. And we're just starting to get into this work. All right, so here's a brief outline of where we're going to go in the seminar today. We'll talk about sort of some background on lithium, supply chain issues, and sort of the transition here in Oregon. We'll go over some critical mineral information, sort of set the stage for that and the Earth MRI program run by USGS. And then we'll talk about the geology of lithium deposits, the source rock types, where the lithium comes from, how we create economic lithium deposit, so the lithium recipe. And then as a structural geologist, first and foremost, I'm always interested in how structure plays a role in developing these deposits. And so we'll talk about the different settings that they form in. And then we'll just look at a couple case studies that are not too far from here. One, the Rhyolite Ridge deposit in southwestern Nevada. And then we'll end with some geology of McDermitt caldera and what we're doing and learning there. So let's jump in. So what's the big deal about lithium? Well, I'm sure you've heard about this, if not recently, then sometime in the past, decade or so. We've really hit the ground running and now blazing forward with battery technology that's based on lithium ions. So this is really crucial for rechargeable batteries that powers much of modern technology, from smartphones to EVs and to grid storage systems. And as everyone, around the world is starting to recognize, this need to transition away from fossil fuels for the carbon impacts, lithium-ion batteries are really essential for storing that energy, whether it's from solar and wind or other renewable energy storage systems. And so EVs, major driver of the lithium demand. That's really the prime motivation for getting lithium resources online and finding more of these deposits and understanding them so that we can bring them into manufacturing for EVs. And so across the board, really, lithium is playing a vital role in Oregon's energy transition, and it's really central to addressing the impacts of climate change. We're not going to talk a lot about economics, but I want to give a little background. So demand for lithium is soaring, and this is a chart made in 2020 looking at the outlook for demand for the next 15 years. And the takeaway here is that when you consider EVs and energy storage systems, every year over year, there's a forecasted 20% increase in the demand for lithium. Most of this comes from, grid storage and EVs. And, sales numbers are in from 2025. Globally, there were 21 million EVs sold last year. And that was almost exactly a 20% increase from 2024, which was 17 million. And that was 20% over the year before, which is about 13.5 million EVs. So these aren't just projections. We're actually hitting these marks, at least in the first 5 years of this chart. And, by 10 years from now in 2035, demand will be 3 to 4 times higher than it is now. And so we're already seeing that coming true in these first few years since these forecasts were made, and it's going to continue into the future. So demand is on the rise, but the supply is struggling. Now, there have been some price fluctuations recently. Not going to get into that too much, but in the present day, supply is a little bit outpacing the demand. A lot of projects came online in the last few years that have kind of shifted that, and so the price dropped. But really, the long-term trend is that we don't have enough recognized resources to really meet the demand that we're going to see. So these are numbers from a couple of years ago, but basically there are 4 main players in the world in terms of lithium production. It's mostly Australia leading the way, and then Chile and Argentina and China with about 20% of production. And the rest of the world, including the US, is very minor compared to that. Now, if you flip this around, and this is talking about production of lithium, but if we talk about refinement of lithium and processing of lithium, China actually controls 70% of the refining capacity. So almost all of this lithium, from any of these countries, gets passed through China to get processed, and that's a major issue for the supply chain and national security here in terms of securing these assets and having a domestic supply of them. So, China is a big player, and the U.S. is barely on the chart. And then one way to look at this, I like this graphic, but there's a lot going on here. Basically, if we look here. Get a laser pointer here. I'm going to get my pointer out. So this is sort of 2030 projection of total global production, 1 million tons of lithium. So this will be the projected production if all the resources that are kind of on track to be developed actually do come through and get developed and all those mines get opened. 2030, we're looking at 1 million tons produced, but the demand by then will be about 3 million tons per year. And so that's, again, to keep up with sort of the driver from EVs, which is sort of projected 40 million or so EVs sold by 2030 annually. And so we're looking ahead at this gap, this widening gap between what's going to be available and what the demand will be. And so it's 3 times more demand than supply. Even if you take all of the projects, for lithium resources that have been recognized, even the ones that were just discovered yesterday, and add all those up and assume that they could start producing in the next 4 years, which is kind of fantasy for most of them, that would only hit 85% of the total demand. So we'd get closer to this value in 2030, but we're still not even going to approach it without either improving technology or finding new resources that have not been discovered yet. So this is the real issue when we talk about economics. And the supply chain is also a problem. So I mentioned China controls about 70% of the refining capacity. It's the resources and the refining that China does not have alone. I mean, the U.S. has now recognized many resources that exist, mostly in the Western U.S. And what I'm showing here, all of these in orange are current lithium capacity. So either resources or refining. And basically, if you look at just the orange dots here, this is where lithium is and is being mined and where it's being processed out here in North Carolina. So there's 2 processing centers in North Carolina. They're very small volume. Those are the only ones that exist in North America. And there are 2 deposits being mined today in economic quantities. There's in Quebec, this is a hard rock mine, so pegmatites. And then out here in southwestern Nevada, the Clayton Valley area, there's a brine system there that's been mined for the last several decades, but not much produced from there. Again, this is less than 1% of total global production. And so in blue are, planned refining additions to our refining capacity, and processing centers on the East Coast. These have not been started yet, but they're in the works. And then in blue in the Western US, these are some of the other big resources that have been found down in the Salton Sea, down in Southern California, and mostly in Western Nevada and Southern Oregon. And so there's a lot, this disconnect between where the geology occurs and where the lithium actually is and where the processing can take place. That's the real crux of the problem with the supply chain. And so a lot of the efforts in the last decade or so to correct this and bring refining and production to the US is to address this problem of domestic resource security. So let's talk a little bit about critical minerals. This has been kind of a buzzword for the last 5 or 6 years. And when we say critical minerals, we're talking about depends on who you ask what the definition of a critical mineral is. But all of these things on this table highlight what, at least in 2022, this is a DOE figure, represents a critical mineral. And now really these are elements, but when we say critical minerals, we mean the minerals that have these key elements in them. And this list was updated last year. USGS has a list that is very similar to this, but things that were added are things like lead and rhenium and a couple other things. But there's about 50 or 60 elements that are considered critical. And this is one definition that a critical mineral is a non-fuel mineral or material that's essential to economic and national security, has a vulnerable supply chain that can be disrupted, and that serves an essential function in manufacturing or production of a product, or that would lead to significant consequences if that element was no longer available. And so that's kind of what defines whether something is critical, if it's prone to disruption and if it's really used as an essential function in some manufacturing. And so this is that's kind of the state of what's defined as a critical mineral today. And if you want to know where critical minerals are, you don't have to look any further than your pocket or your computer on your desk. So more than 50% of all the components in our phone come from mineral commodities. And most of them are actually critical minerals by most definitions. So this is all these are, this graphic kind of nicely shows the rocks and talks about the different critical minerals or critical elements in them. You know, this is everything from the gallium that comes from bauxite that is put into the LEDs in your screen, to the tungsten from wolframite that serves as a heat sink and basically the weight to counterbalance when your phone vibrates. So there's you have tons of critical minerals on you right now, and lithium is one of those, which serves as an essential function in the cathode to carry charge. And so demand for these and many other resources are on constant rise in the US and globally. And so, you know, there's been a huge effort to try to understand the critical mineral potential, especially domestically. And it's not just lithium that goes into an EV. There's actually lots of metals, most of them critical, to make one battery for an electric vehicle. So, you know, lithium is here. You know, this graphic is kind of showing lithium down here. It's really only 3.2% by weight of the metal in an EV battery. You actually need about 5 times or 6 times as much aluminum and about 10 times as much graphite and, you know, about 10 times as much nickel just to make one EV battery. So lithium is critical, but it's most of these that really, it's going to take a kind of all of the above approach to really fund this green revolution that we're starting now. And good news for Oregon is that all of these that I've highlighted in green, which are kind of the most significant components by mass in the batteries, all of these are known to occur in Oregon or have historic mining in Oregon. All right, so let's just talk a little bit about Earth MRI. So this is the Earth Mapping Resources Initiative. So as I mentioned, we rely heavily on foreign resources for dozens of these critical mineral commodities, the vast majority of them. This started back in 2017 with an executive order that mandated federal agencies ensure a secure and reliable domestic critical mineral supply. The next year in 2018, the U.S. Geologic Survey launched the Earth MRI program to fund geologic mapping specifically aimed at identifying areas with critical mineral potential. And so this, you know, approach was to provide funding and resources and data to understand all kinds of things from LiDAR data for topography to geologic mapping, big aerial geophysical surveys to look at subsurface structure to try and understand potential, geochemistry data sets nationwide, funding of mineral deposit databases, borehole catalogs, all kinds of things, just trying to capture as much data and fund as much science as we can to understand the potential domestically for critical minerals. In 2021, so a few years later, the Earth MRI program got enhanced funding, about $320 million, through the bipartisan infrastructure law, or the Infrastructure Investment and Jobs Act. And the overarching goal of this has been to reduce our mineral import dependence. So, you know, this really, ultimately, the goal is that this will lead to, strengthening our national security, creating jobs, a lot of rural jobs, and stabilizing these domestic battery supply chains that don't exist right now. And so this is sort of a snapshot of the whole country, kind of painted by these critical mineral systems. And so the USGS has done a lot of work to identify and characterize all these different mineral systems where critical minerals can occur. And so each different color on here is a different mineral system. Here in Southeast Oregon, this blue blob here and down into Nevada and all across the Great Basin represents the lacustrine evaporite critical mineral system. And this is the system that is associated with lithium deposits, whether it's from brines or sediment-hosted lithium. And they really are forming in these sort of basins in the Western U.S., these sort of arid, high and dry basins where we can get evaporative concentration of lithium and other minerals like barite. And so in Oregon alone, we're doing work to kind of refine the full footprint of these mineral systems, but there's at least 8 of these critical mineral systems in the state. And so there is significant potential, mostly in the Klamath Mountains and the Blue Mountains, sort of where the old rocks are in the state for a lot of these. But southeastern Oregon is really a key area for particularly this evaporative lacustrine system. And more probably exists. This is not exhaustive, but this is, kind of the state of our understanding of these mineral systems across the country. All right, let's talk about the different types of lithium and global sources of lithium. So we kind of get 3 different sources for lithium that can basically provide economic quantities of lithium that can be mined. In this map, they're kind of color coded to match these 3 types. So by far the most dominant is hard rock mining. These are pegmatites, these are igneous systems, and really, it's the whole map here essentially. But Australia, especially, and Central Asia are kind of the focus areas for where most of this hard rock mining is done. Brine extraction, so extracting lithium from saline brines, is another major player in sources of lithium. The biggest concentration by far is the high Atacama Desert area in northern Argentina and Chile, but also in Nevada, that one producing mine in southwestern Nevada is a brine system. And then clay deposits are the new kid on the block. I mean, not so new anymore, but they're the only one that hasn't had historic production that we're really starting to develop and understand now. And so clay deposits, where lithium is locked into the structure of clays, this is really in the exploration phase. We don't have any production yet, but a lot of projects are lifting off right now. And the key areas for this are really the Western US, Nevada, Oregon, and California being the main players here. There's a jadar deposit in Serbia. There's some in China, but really most of it is in the Western US, at least the large deposits that we know about. So let's just take a little closer look at each one of these. So hard rock mining, the one that's been around for the longest and provides most of the lithium on the market today. This is mining that extracts the silicate mineral spodumene. This is a lithium-rich pyroxene. But it's basically in granitic rocks and really mostly pegmatites. And so the Greenbushes mine in Western Australia, that is the big one. That's where more than 30% of the production of lithium, more than 30% of the lithium, likely some in your phones, and mine too, came from this mine. So this is a real big player. It's been operating for a very long time. It's a big open pit mine out in Western Australia. And so there are lithium minerals like lepidolite, this beautiful purple mica. And then this is a really large spodumene crystal, lithium pyroxene. And this might be the biggest one I've ever seen a picture of in my life. This is a giant spodumene from an outcrop quarry in Maine. So really high grades in these rocks. This is sometimes 2 weight% lithium in these. So really high grades, but small volumes. So you can see, the pegmatites in this mine, they're not guaranteed to be everywhere. So mining is a little more expensive. There's a little more lead time to go develop one of these mines, 10 to 17 years in most cases to get one of these up and running from discovery to production. But bang for your buck in terms of grade when you find one of these deposits. Second source, brines. This is, the extraction of brines, pumping groundwater from the subsurface. that's rich in total dissolved solids, and predominantly this is making sort of lithium salt or lithium chlorine by evaporating it in ponds. So we pump water up from underground, spread it out in these evaporative ponds, and just let them sit there and evaporate. Has to be in a dry, arid climate to really be effective. And then the lithium ore gets concentrated in these sort of lithium salts. And so this is a little photo from the Atacama Desert, a really big operation up there. And this is the operating Silver Peak mine out in Clayton Valley in southwestern Nevada. So in this case, this tends to produce sort of moderate grade, low to moderate grade lithium. The time is the real issue here. It takes a long time to just let that pool of water sit and evaporate to concentrate the lithium. So hard to speed the production up here. A lot of time investment, but it tends to be a little easier to operate and get started. Just waiting around for the lithium to concentrate is the critical part. And then the third one is the clay deposits, and that's really what we're going to focus on today. So for clay deposits, we're talking about just run-of-the-mill mudstone. These are very fine-grained clays that have lithium bound up in the structure, usually the octahedral layer in the clays. It can be in the interlayer spaces, but it can easily be let out. So lithium is very incompatible in melts, and it's very fluid mobile once it's out of the melt. So it gets bound up in the clay structures, and some clays are better at holding on to it. So this is a nice SEM image of a illite. So this is a non-swelling clay, and this is where you get really high grades of lithium because you can lock more lithium into the structure when it's not one of these swelling smectite clays. And so again, we're up in the 2% weight percent lithium in this clay. That's getting up towards pegmatite concentration. So in the hard rock mines, we're looking at similar grades if you have a nice illite clay. Smectite, you're going to have a lot less than this, about a fourth as much lithium in the swelling clays. And then this is what it looks like. These are some cores from the Rhyolite Ridge area. These darker gray bands are the lithium-rich clays, and the white can be either, carbonate inner beds within those or inner layers. And anywhere you have clay, if you have a source for lithium, you can trap that lithium within the clay structure. So these can be really high grades, but they're typically moderate grades. And they do we're noticing, with the early development that we can really start the production of these, especially if they're near the surface, a lot sooner. This is just basic surface mining. A lot of these deposits that are known are right at the surface, like this example at Rhyolite Ridge. So basically we're just picking up the rock, crushing it up, and dissolving it in acid to leach out the lithium. Now that presents all kinds of host of other problems. It's not easy to pull one thing like lithium out of a clay. It takes a lot of acid, a lot of water, so it's resource intensive. So none of these sources is without issue. But clay deposits tend to be more easily accessible. Those are the surface. And we're starting to do some R&D and understand the best ways to process these to get the most recovery out of them. But again, this is kind of the new player, and so we're learning a lot as we go in terms of how best to access and prove up and then process these resources. And so who's got the biggest resource? Well, everyone measures it a little differently, but by most metrics, Oregon has the largest deposit that's known in terms of indicated resource. So this is a list from a couple of years ago, but the order of these hasn't really changed. This is measuring total resource and lithium carbonate equivalent. That's a common measurement. But the resource at McDermitt on the Oregon side, which is unfortunately just called the McDermitt deposit, but that one is the largest by the estimates, at least from 2023. Thacker Pass is number 2. I think they might argue that they have the most. It's higher grade in the south. We'll look at it a little closer later, but the 2 deposits combined at McDermitt Caldera far surpass any other deposits that are known in terms of resource estimates. And then the other top 5 are mostly in Nevada. There's one in the Congo, that's a pegmatite system, but the others are all sediment-hosted systems that have not yet been developed. And so we have the resources in the Western U.S. What we do about them and how we responsibly, try to manage them and understand the potential there. That's really the step we're at right now, as these companies are trying to move from exploration to development. All right. So how do we make a lithium deposit? Well, there's a very specific recipe for at least a sediment-hosted lithium deposit. And so those terms, claystone, lithium clay, sediment-hosted, they're kind of used interchangeably. I think sediment-hosted is a better term because it's not always bound in claystone. Marls and other clay-bearing lithologies can host lithium. So if we want to make one of these sedimentary lithium deposits, we need three things. We need a source of the lithium, and this is almost always a rhyolitic magma or volcanic rock. So granites and rhyolites are the source of the original source or primary source of lithium. Lithium is highly incompatible, so it tends to stick around in the melt until it can't anymore. And so pegmatites, late stage granites, rhyolites, high silica rhyolites, I mean, these tend to be the most abundant in lithium. It's not completely absent in more intermediate rocks, but you really get them concentrated when we're up in the sort of late stages of this or with minor partial melts. So you need a rhyolite or a granite as a source. Um, and then we need something to transport that. So we can have a source of it in a rhyolite, but we need water to help pick up those fluid mobile elements like lithium, move it out of the rhyolite or the granite, and transport it either via groundwater or hydrothermal fluids. So once we have a transport mechanism, we can pick that lithium up, move it to a structural trap or a lithium trap, which is usually a closed basin. So we do this, humans do this with the brine systems. We pull that lithium out of the groundwater where it's in low concentrations, and we let it get concentrated in its own little basin at the surface. Well, nature does this too. So closed structural basins allow that natural evaporation and evaporative concentration of lithium in lake sediments. And so any structural basin that's closed, hydrologically closed, so water doesn't get out, can be a trap. But calderas kind of give us all of these things in one. So caldera is where you go to get this three-course meal, if you want. So we got a source with magma at depth, and if it's something like McDermitt, it's a very high silica system and involved system. We have transport processes with hydrothermal fluids and meteoric fluids, and a nice closed basin, that forms after the caldera collapse. You kind of have all the ingredients here. So this is a great, all inclusive system, but it's not the only one where lithium forms. So extensional tectonic basins can also do this, and Southeast Oregon has lots of extensional basins. If you ever driven around out there, it's nothing but ranges and basins in between them. And those basins, here I've kind of blocked out the rest of the state, but this is all of Southeast Oregon. And you can see, wherever we go to look around the basin and range, there are extant lake basins today. And in the Pleistocene, they would have had much larger shorelines when the climate was wetter. And so this light blue is kind of highlighting the extent of these lake basins during, say, Pleistocene time. And so there are a lot of lake basins that are formed by extensional tectonism crustal thinning that can serve as lithium traps. Whether there's a source and transport mechanisms is not yet known. So there are no known prospects out here besides McDermitt caldera, but we have the structural setting that could form these deposits. And so understanding the potential there is a goal. And so instead of a caldera system, which you can kind of, it can be your lithium starter pack. It has all the ingredients. If you have a lithium source and a little bit of fluids moving them around, extensional basins are just as good. I mean, a caldera is kind of, it's similar to an extensional basin where you've got subsidence and maybe internal drainage. But it's different in terms of the symmetry of the basins. But they're just as good if you can form one that's closed, at least for a period of time, you can create those conditions needed to generate the lithium deposit. So yeah, Oregon has the potential, at least with the structural traps. The other thing we have is calderas. So this map, all the little rings are known calderas in the state, and there are some that are less well known or exposed than others, but all of these are documented. And in red are rhyolites and sort of high silica or felsic volcanic rocks. So these are in red everywhere where we have sort of rhyolites at the surface, Cenozoic rhyolites, and then in blue are all of the sedimentary rocks. So if we're talking about ingredients here, I mean, excluding transport, Oregon has lots of the things that we need to maybe develop these deposits. Again, the only one we know about is McDermitt caldera. It may be the only one, but we have a lot of the right geology to go and look for the potential out here in these other places. So McDermitt caldera is down here. That's where the main lithium deposit that we know about. It's really just barely in the state, but all this geology is telling us that we have a good chance of at least exploring and trying to find more. And so it really takes a lot of work to prove up whether there's resources there. But that's part of the Earth MRI program is designed to understand the potential through all of these sort of techniques here. All right, that's a lot of background, but now I think we're ready to look at a couple case studies. And so we'll get to McDermitt, but I want to just to compare and contrast these dual structural settings where we could develop these sedimentary lithium deposits. Let's take a look at Rhyolite Ridge in Nevada, where I did some work when I was at the Nevada Bureau, funded by the Earth MRI program. So we'll start looking at Rhyolite Ridge at a tectonic basin, and then we'll switch to McDermitt to look at the caldera-hosted lithium basins. And we published a paper last year in Economic Geology that kind of really focused on Rhyolite Ridge, but kind of set up this two setting framework for the structure of these basins. All right, Rhyolite Ridge. So here we are. There's a little location map here. This is the state of Nevada. Here's McDermitt caldera in Oregon, kind of at the top. And then Rhyolite Ridge is down in southwestern Nevada, about halfway between Reno and Las Vegas, very close to the White Mountains in California. So there's many lithium sedimentary and brine prospects across the region. Those are shown in the green and blue stars. This Silver Peak mine. That's the one I showed a picture of. That's the one operating lithium mine in the U.S. today, and it puts out a fraction of 1% of the total global production of lithium. So this is the deposit here. This is the Rhyolite Ridge area. This is the Silver Peak Mountains. I'm not going to go into tons of detail here, but this area has a fascinating geologic history. You can see there's metamorphic core complexes exposed through here. There's a long history of low angle extension, really large magnitude extension. And today you see all these strike slip faults. This is within the Walker Lane Belt, this zone of dextral transtension that's part of the Pacific North America plate boundary. But that's a talk for another day. So if we're just looking at Rhyolite Ridge here, the deposit, which is in the Cave Spring Formation, this is the sediment-hosted lithium. It's shown in blue here, and it's just in this one basin, at least where it's being worked on now. It's just in this one little basin right next to Rhyolite Ridge. And so, there's a lot that we don't understand about the system. But since the lithium was recognized in it about a decade ago, it really started to get worked on in the last decade. Things like the source of the lithium and boron. There's a really significant boron resource in these sediments. The source is not really known. The transport mechanisms aren't understood. And the structural setting has been questioned. There's been some suggestions there might be a caldera underneath this basin, but it really hadn't been looked at in detail. So that was the goal of our project, was to go there with the Earth MRI program funding to make a geologic map at 1 to 24,000 scale, a nice detailed map, build a stratigraphic framework, and really do some detailed work on understanding the lithium system there, all aspects of it. So we produced a geologic map that you can get from the Nevada Bureau, and this economic geology paper kind of summarizes a lot of the geochemical results from looking at the source rocks and the lithium resources. And so this stratigraphic column, we can kind of skip over the bottom half here. So there's some Cambrian strata, some early and middle Miocene sedimentary and volcanic rocks. But the real interesting part, at least for the lithium story, is up here at the top. So these are latest Miocene, Pliocene, volcanic rocks, and then overlying lake sediments. And so we've got lots of dates from these underlying volcanic rocks. This is the Rhyolite Ridge Tuff. This is a lithium-enriched tuff. It has concentrations of lithium about 10 times higher than most rhyolites. It's not a ton. It's not economic to mine the rhyolite itself. It's not that concentrated, but compared to a typical rhyolite, it's got a lot more, several hundred ppm lithium, which is almost an order of magnitude more than an average rhyolite or granite. And then there's also some kind of more latite or trachytic volcanic rocks that are on top of the rhyolite ridge. This is the Argentite Canyon Formation. Both of these are about 6 million years old, 6 to 5.8 million years old. So they erupted in pretty quick succession. And then right after that, they're overlain by a couple hundred meters of lithium enriched and boron enriched sedimentary rocks. These are lake beds, and that is the target for the lithium mining out there. So it's this cave spring formation shown in brown, and the basin is really right in the middle here, and stippled kind of there to show where the lithium bearing rocks are. And so let's take a look from the field. So this is kind of this is one of the best views. This is the discovery outcrop of the cave spring formation lithium boron deposit. And so that's this white rock in the foreground. These are lake sediments. You can see nice thin beds there. This is more of a marl facies, which is just a mix of carbonate and clay. And so that's where most of the lithium is hosted, in clay stones and marl. The boron is hosted in a sodium borosilicate cearlacite. And so both of these are in pretty high concentrations. That's kind of unique for this deposit. You get two critical minerals for the price of one. Most lithium deposits don't also have boron, but this one is economic for both those reasons. And so these rocks are dipping towards the sort of middle of the Cave Spring Basin. And in the background here, this is Rhyolite Ridge, the namesake for the Rhyolite Ridge Tuff. And that's this entire mountain is Rhyolite Ridge Tuff. This is the 6 million year old lithium enriched tuff. It's several hundred meters thick. This is a big deposit, probably close to where it erupted, but it's sitting right there under the basin, along with the other latite flows. And that's probably the main reason why there's so much mineralization in these overlying lake sediments, because the source rocks weren't, miles away. They were right underneath the basin. And so, in the interest of time, I'm not going to go through all the geochemistry, especially because I'm not a geochemist, but we did a lot of work looking at those volcanic rocks that sit right under the lake sediments. We wanted to understand whether they could have served as a easy source for the lithium in the lake beds. And so, we don't notice a lot of alteration in the rocks, which is interesting. If we leached out a bunch of lithium, we'd expect to see a lot of evidence of hydrothermal alteration. And there was some, but it was very weak and spatially heterogeneous. So we saw a little bit of sericite, a little bit of carbonate and K feldspar, but it was very minor overall. And so there could have been some hydrothermal fluid inputs and sources of lithium and boron early in the basin history, but we really don't see evidence of that, at least from right within the basin, from drill holes and from the outcrops around the periphery of the basin. And then, here's a little cross section just across the Cave Spring deposit. So in brown, this is all the lithium enriched rocks, and that dark brown is where the main ore zone is. So that's the highest lithium and boron concentrations. And, both drill hole and outcrop samples indicate that the mineralization is stratiform, meaning it's not just in local pods. It actually is within discrete beds, and particularly this zone in the middle Cave Spring formation. So this dark brown middle unit has the highest concentrations of lithium, boron, and other things, magnesium, sodium, other things we'd expect to also be fluid mobile. And so it's telling us we can see these beds and we can correlate them across the basin. So this really suggests that, the mineralization was related to the conditions in the basin that affected the whole basin, not just how close you were to a hydrothermal vent or something. So this was really important to kind of compare the lithium concentrations within the sediments, and notice that actually when we look around at all the different drill holes, we can find the same ore zone with a similar concentration all throughout the basin. So it's really reflecting those conditions. And then a little bit more chemistry. So on the left, again, same color scheme. Brown are the lithium-bearing lake sediments. And these plots on the right are kind of the underlying rocks. And so this is the latites in the Argentite Canyon. This is our Rhyolite Ridge Tuff. And then these are some older sediments of the Silver Peak or Esmeralda Formation. But we can see a couple trends here that are really interesting. First, there's a really strong similarity in enrichment in mobile elements. So this is the lithium, boron, arsenic, antimony, other things. We see the same elevation in these mobile elements as in the source rocks. And also, other things like transition metals are depleted in the source rocks, or potential source rocks, which we really think are the sources. And we see the same depletion in transition metals. So a lot of similarity in the chemistry of both the sources and the sink, or the lake sediments. And then when we take an even bigger picture sort of view at total enrichment relative to typical continental crust, so these are all relative values of all these different elements compared to typical continental crust. And excess is in green and depletions are in red. So the main thing to note here is that we see average enrichment factors for these things like these fluid mobile elements that are 30 times higher than typical upper continental crust in our lake sediments. And in some cases, they're up to 325 times higher in the main ore zones. We see tons of lithium, way more than you expect in a typical rock in the upper crust. And so all of this to us suggests, this is our working hypothesis, that the lithium and boron were sourced directly from those underlying volcanic rocks, and they were on the periphery of the basin too, but from just simple supergene weathering or meteoric water leaching out slowly but surely, pulling these lithium and boron resources out of the volcanic rocks and then depositing them into this lake basin that was closed, and then evaporative concentration led to incorporation of lithium within the lake sediments. That's the story we're pitching in our paper, and a lot more work needs to be done. This is just the first time we really looked at those potential source rocks from right under the basin. Most of my work here was on the structure. I'm not going to have a ton of time to get into that, but I will just say we did a lot of work mapping the structures out here because it was not very straightforward what was going on in the basin. And so, there was a lot of evidence of really significant faulting. This is a cross section across the Cave Spring Basin here. So this is the lithium-rich rocks in brown. This is Rhyolite Ridge in that photo we were looking at. This is kind of looking across the basin to Rhyolite Ridge. And we mapped some pretty significant structures that we think have been broken up by later faulting. I can't walk through all of it, but we see really good evidence of major fault zones and pretty significant throw on some of these faults. But there's actually two systems of faults. There's some that dip towards the east, and then a younger, higher angle set that dip towards the west. And what we've noticed with these is that we can map these from the surface, but some subsurface data is always helpful when you're trying to map these structures and test your structural model. So this is electromagnetic data. This is flown from a helicopter, about 100 meters above the ground at the most, and it's basically showing the electromagnetic properties of the rocks down to a few hundred meters depth. So we're getting information about the resistivity structure of the Earth here, and in a nutshell, high resistivity, reds and purples, volcanic igneous rocks show up as really high resistivity. The things that show up as really cool colors are the really low resistivity or conductive layers, and these are things that have either pore water in them or that have clays. So clays always show up as really, really low resistivity, which are these really cool colors here. So they're very conductive. All those extra ions in there from the lithium basically create this response here in the conductivity. So they're showing this proclivity to have these ions trapped in the clay structures and or pore water or brines, but that's what's showing up here. And we see our Cave Spring deposit. It's a really nice blue conductive anomaly. And then we can see our Rhyolite Ridge tuff, down here and getting truncated on the basin margin by this is a view towards the looking kind of north. So these are west dipping faults that break up the basin. And so this has been really helpful for us for developing our cross sections. Again, this is funded by Earth MRI, really useful for looking at a little bit of subsurface data all across this basin. And we have very tight line spacing all across our study area, which really helped us with the structural mapping. But you can see there's not just deposits here in Cave Spring. There's actually some other younger basins, faulting step to the west through time here. And so these younger basins, these are late Pliocene, Pleistocene basins. There's potentially some prospects in these basins that may not be at the surface, but may exist down at depth a little bit. And some borehole data suggests that too. So this has been really useful for identifying other areas of prospectivity. And we have a little bit of a cartoon here. I'm going to kind of walk through it, but basically long period of extension in the area. The story starts with the lithium when the Rhyolite Ridge tuff was deposited. So this was a big regional ignimbrite. And then we had formation of the Cave Spring Basin here as a half-graben basin in a big east-dipping extensional fault. And so this normal fault allowed subsidence and then concentration of the lake system here and hydrologically closed system that allowed this enrichment of lithium in the basin. And then the structural story there, told through fault kinematics and really detailed mapping, is that the mode of extension switched in the basin, and we started to have high angle faults that activated from east to west. So we have this westward younging of extension through time, and the Cave Spring Basin got broken up a little bit. And as we moved into the present day, the faulting migrated to Fish Lake Valley, and then the faulting is active. There's a very active Emigrant Peak fault zone on the east side of Fish Lake Valley that's active today. And so we think this is a really classic example, kind of like if you're familiar with the Yarrington district in Nevada, which has had multiple phases of extension, first on high angle faults that got rotated and then chopped by a second phase of faults. This to us looks like a classic example of that, just purely extensional basin and a really rich lithium deposit. So, calderas are great, but tectonic basins, if you got all the working parts and an active magmatic system, we can really generate significant lithium deposits. All right, so that's a tectonic basin. Let's talk a little bit about McDermitt. I realize I'm running low on time. I don't want to go too late here, so let's make sure we focus a little bit on the star of the show. So McDermitt caldera, I'm sure many of you are at least familiar with the Yellowstone hotspot. To say it in a few words, McDermitt is the first place the Yellowstone hotspot landed and made its debut in North America. And so today the hotspot is over here in northwestern Wyoming. That's where the Yellowstone plume is underneath there. And so we have active magnetism there. But you can walk back in the Snake River Plain to these older and older calderas till you get to McDermitt. And this is, this area and the caldera systems here are where the first explosive rhyolitic volcanism happened related to the Yellowstone plume. And since then, the plate has moved westward over this relatively stationary plume, and that's why we have this kind of extinct trail of calderas leading back to the active one today. And so it really showed up here, and it must have been a sight to see, a fireworks show, to say the least. And so the other thing that happened with this arrival of this plume, the Columbia River basalts were a massive outpouring of this large igneous province, this huge flood basalt province that just poured a huge amount of magma out all over eastern Oregon that flowed down the Columbia River Gorge and Proto Gorge and out to the ocean. And so it covers a huge area in eastern Oregon and Washington. And it's not just basalts that are the product of that Yellowstone plume. McDermitt owes its whole life to it. All right, so here's a summary geologic map of the caldera. So this is a really big system. This is about 35 kilometers wide, or about 20 miles, and about 45 kilometers from north to south. So this is a really big caldera. This is a simplified map from Chris Henry and Steve Castor. And if we just take a kind of quick look at sort of the Oregon side, this is just a cross section kind of through the margin, the ring fault system. You can see we have a pretty nice structure, this stack of Steens basalts and some interbedded tuffs. And the McDermitt tuff outflow is just on the very cap here in the eastern part of the caldera rim. And then this big pink deposit here, this is the intracaldera tuff. So this is the ash that landed back in the caldera after the super eruption. And it's several hundred meters thick, about 500 meters thick where it's exposed on the western margin of the caldera. And then there's some post-caldera lavas shown in red here, the Aurora lavas. This is this bright red unit. And then the resource, the lithium-bearing strata, are this little orange patch right on top. It's only a few hundred meters thick at the most. It's typically only a couple 100 feet thick. But it is really significant in that it is outcrops over most of the basin, especially on the periphery. So all of these orange colored rocks on the map are the sedimentary rocks that host the lithium. These are the lake beds. And so even though they're pretty thin, in terms of the whole thickness of the caldera fill, that's where all the lithium is concentrated. And so that's what these mining companies are really interested in here, is just this cover sitting on the caldera floor. And so there's been some work by Tom Benson and others and Chris Henry, but this is a figure from one of Tom's papers from 2023 showing some geochemical data from the clay deposits. And lithium concentrations are not the same depending on where you look in the basin. So unlike Rhyolite Ridge, we see local variability, and it has to do with what type of clay was deposited there. And so in the north, we have a lot more volume of sediments, but a lot lower grades. So this is Jindalee's area, the company that's operating there. Down at Thacker Pass on the Nevada side, there are lower volumes, but much higher grades. So this is the 2% by weight lithium in the illite-bearing clays down there. So depending on where you are, you have different grades, and they've done some nice work to show that lithium concentration, which is kind of these black circles here increasing to the right. We see highest lithium concentrations associated with the lowest clay D spacing. All that means is illite. So illite has a much tighter, compact structure than smectite, which is a swelling clay. And they see a really nice correlation between the clay type and the lithium concentration. And that just We've known about that prevalence for lithium to be more bound in greater abundance in illites, and they're seeing this in their data from some of these boreholes in Thacker Pass. We don't have any illite on the Oregon side. At least I haven't seen a whiff, and neither has anyone else that I know of. So it's interesting that there's some spatial variability in this. It doesn't really matter from the mining companies because there is a great volume of these rocks on either side. And so they're going after it on both sides. And I just want to highlight the size of this caldera because it is not tiny. This is a map of the Portland area, and to scale, the McDermitt caldera on top of it. So, if you want to drive across the caldera, you could start north of Vancouver and take I-5 all the way south past Wilsonville, and you'd still be in the caldera. So this is really a big feature, and there are big lithium deposits of different grades all around it. And for another comparison, here's everyone's favorite lake. Crater Lake is a big crater, big caldera, but it's kind of a drop in the bucket in McDermitt. So this is an unusually large system, and as far as lithium goes in calderas we know about in the Western US, it is the only one with anything like this in terms of lithium concentration. So it is a real anomaly, and we're still trying to understand what makes it so unique. And so this is another great kind of summary diagram by Tom Benson and others. So this is a cross-section cartoon across kind of north to south across the basin. So this is the Oregon side on the right and the Nevada side on the left. Here's the Thacker Pass area. This is where Lithium Americas is operating. These are the really high-grade illite-bearing claystones. And then this is Jindalee's deposit over here on the north side in Oregon. And so this is one model. We're not, there's still a lot of debate and research going on to try to understand the mechanism of enrichment of these. But Tom and others really think that the South is reflecting sort of all of the above when it comes to transport pathways to get lithium into that southern part of the basin. And so all these arrows are showing sort of fluid pathways. And you can see in the South, they get all three, the green, the orange, and the blue. And so this is meteoric water, just from, rainwater, groundwater, just leaching lithium out of the McDermitt tuff and other rocks and bringing them into the basin. There's also input from just tuff degassing. So right after the pink McDermitt tuff landed back in the caldera, there's lots of volatiles, lots of gases that were getting exsolved out of solution. So losing those gases are basically lithium is coming out with that process. So the super hot tuff after it landed in this basin, as soon as we developed a lake, would have been receiving lithium from just devolatilization of the tuff. And so that was happening across the basin. But what they think is unique about the South is that there was this extra orange arrow here, which is sort of fluid pathways related to hydrothermal fluids. And so what they argue is that there's magma resurgence. There's a big resurgent dome in the middle of the caldera that's lifted up after the caldera formed. And they think that the illite in the South is related to extra hydrothermal inputs of lithium that would explain both the formation of illite. You need hot fluids to form illite. I mean, it's a temperature-controlled process to do that. And that also brings with it extra lithium and potassium and other things that allow you to build that illite structure. So they think this hydrothermal system was really significant in the South and didn't even really express itself in the North to explain the lack of illite. There are lots of problems with that. It does make sense at a big scale that maybe there's more hydrothermal alteration in the South. But what I didn't mention was that in the North, there are historic mercury mines there. So there are some pretty significant mercury deposits that reflect hydrothermal systems that were active at some time, after the caldera formed. But we see evidence of hydrothermalism in terms of the mercury system, but there's no illite there. So I'm still, out on why the South is much more higher grade and why we don't see a similar type of illite and illitization in the clays in the North. But this is the things that we're trying to understand through our mapping and our geochemical studies. And it's something that we'll continue debating as we go forward with this. And so we're wrapping up here. I just want to share a little bit of what we're doing at DOGAMI right now. So, I don't have a ton of results about our work. We're in the middle of our mapping. By this time next year, I should have a draft map and a lot more on the geology of the caldera if we want to talk about volcanic stratigraphy and petrogenesis and structure and sedimentation. But for now, we're going through systematically logging cores, with help from OSU and DOE. We have some great collaborations with John Dillis and Brian Tadich and their crew at OSU. Spectral gamma ray core scanning. We've got lots of XRF geochemical assays from the source or volcanic rocks in the pre-caldera stratigraphy and also in the lithium deposits. We've got a laser-induced breakdown spectrometer, a little handheld LIBS device that we've taken out in the field to kind of get readings about lithium concentrations right at the outcrop. I mean, this is just a typical outcrop example of some of these interbedded clay stones and like tuffs and very silicified horizons there. So lots of field work, lots of core logging right now, and we've got lots of data from the caldera. Mapping is underway. We've got lots of samples. LiDAR data has been hugely helpful for doing this detailed mapping. So we've got complete LiDAR coverage here. And this is kind of a draft map showing some of the structural complexity in sort of the pre-caldera stratigraphy in the green. But, McDermitt tuff, it's an outflow tuff at the top of the rim, and then there's this big resurgent dome in the middle of the basin. And we really want to try to understand the relationship between the sedimentation and the resurgent doming, and the relative timing of those to try and understand when, if at all, the hydrothermal system was active in this area. And we've also got some legacy drill core from the 70s that we've recently acquired, and we store at OSU now from these deep drill holes that DOE put in. We've got all of those, and we're systematically going through those, logging them, and dating some interbedded tuffs to try and get an age for the basin, more detailed chronostratigraphy of the basin. And then the last thing I'll show in terms of data, this is hot off the press. The USGS has done so much work, especially the geophysics group, in acquiring this type of data and processing it and making it publicly available. So this is more airborne electromagnetic data. There are lots of lines here. This is kind of an oblique view looking to the north. And each one of these is a profile, and they're at 1 kilometer spacing so that we can really look at the subsurface structure. And the thing that pops out really well is that, these really bright blues are the lithium-bearing strata. We can even, when we look close, see some detail within there to help us try, with correlations and looking at different concentrations of lithium within the sections and compare it with drill data. And that's all things that we're getting underway right now. But it's really valuable data to have. I mean, we can see some similarities and differences, but notice the brighter blues in the north. We don't have the illite up here, but we have this really, really high conductive or low resistivity layers up here. If I just had to guess, I'd assume that this was the more illite-rich section and this was a little less down at Thacker Pass, but it's actually the inverse. So this isn't showing us where the illite or lithium is and where it's not. It's showing us where the clays are, and why the clays are different on different sides of the caldera is what we're trying to understand a little more. So this data is really valuable. We're really starting to pick this apart and understand the basin architecture with it. And here's just one example of a profile. I can't show all of these, but this is a nice example. This is the state line in white here. So we're very close to the Nevada border, but still on the Oregon side. And this is, in these warm colors and purples are the volcanic rocks of the caldera rim and the pre-caldera stratigraphy. And then this is the clay deposit down in the Jindalee claim area. So this is what they're going to be mining. And, it's only a couple 100 feet thick, and we lose the signal. The more conductive the layer, you lose your signal, so you don't get to see under that, which is really unfortunate. But where we have really high resistivity, we can see a little bit lower. But we don't really get more than 400 or 500 meters deep with this technique. But we can start to see some really interesting things. And if I just put a little interpretation on here, we've got the caldera ring fault system, and this is Chris Henry's map from 2017 at the whole caldera scale. We can start to pick out some of these caldera ring faults and match them with the surface geology. We can see the lake beds here. This is the broad doming or resurgent dome of the intracaldera tuff. And then we can also see some other interesting things here on the right. This is something that I'm gonna actually go back out to in a couple of months when I go back in the field and look. It looks like some of these lake sediments in orange up here on the map project down and underneath some of these volcanic rocks. And these are kind of post-caldera rhyolites that came out after the caldera forming eruption. And we think we see some sediments underneath there. It's interesting because we don't notice that relationship anywhere else in the northern caldera. Most of the lavas are underneath the lake beds. And so if there's volcanism after the lake formed and after the sedimentary rocks were deposited, these types of things might help be driving that hydrothermal system that we're wondering where it was or if it was active at all in the northern part of the basin. So I'm going to go out and look at this a little closer. This data is really useful to come out now. It's available online if you want to, play around with it. But it is really giving us new insights. And it's really valuable to have this while we're doing the mapping, not after, so we can go out and address some of these questions that come up. Um, and so I'm going to end with just a couple questions. We're basin architecture and evolution are the main things we're trying to understand. What the mineralization system, when it was active, during deposition or after deposition of the sediments. And then things like fluid transport processes, what the role of meteoric fluids and hydrothermal fluids is still a big open question. You have to have meteoric fluids, just by a mass balance perspective. But the role of magmatic hydrothermal fluids in the north and the enrichment process in the north is still an open question. And then I'm a fault guy, so I'm going out there and looking at faults and trying to understand how those fault systems may have played a role, these post-caldera faults in controlling fluid flow. And mapping is absolutely fundamental to addressing all of these questions, along with geochemistry and geophysics. And with that, I will just put in a plug. We have developed some fact sheets about critical minerals and a lot of other decarbonization geoscience topics: geologic hydrogen, geothermal energy, carbon storage. I brought copies of them. They're all on the back right by the door. If you'd like to learn more, there's a lot of information on there that we covered today for the critical minerals, but there's some other ones that we just generated in the last couple of months. You're welcome to take some of those with you. And if you have any questions, I'd be happy to take them.